The first speaker of the day is Dr. Luis Pedrela. Luis is a lecturer in the Department of Chemical Science and the course director in the Bachelor degree in Science for Industrial Biochemistry. He graduated in chemical engineering at the University of Lisbon in Portugal, and he went and worked in a pharmaceutical industry before joining the SSPC, I think now about 7 years ago. It was a while. He joined as a postdoc and then became a senior research fellow before being appointed as a lecturer and course director. Today, Luis will talk about one of his expertise, which is the use of supercritical CO2 for manufacturing of pharmaceuticals. And with this, I will leave the next 30 minutes, 40 minutes to Luis.
Okay, thanks, Matteo. And thanks for the invitation to present at the Bernal seminar series. So I need to start with sharing my screen. So let's see if this works. Okay.
Perfect, we can see it.
Yeah. So I'll just go full screen, and then hopefully you would also be able to see it. Yeah.
Yes, all fine.
Okay, so my talk today will be focused on one of.
Hi, how are you?
Sorry, Anya, you're unmute. Yeah, so my talk today will be focusing on one of the aspects of my research activities, which deals with using carbon dioxide, a supercritical CO2, to control polymorphism and particle size of pharmaceutical drugs. And it will be focusing particularly on batch methods, so methods that are used in supercritical CO2 technologies that work in the batch mode of operation, and in continuous methods. So these technologies have been addressed in the literature over the last 20 years or even longer, but have never seen really a fair industry implementation. I mean, supercritical CO2 has been there in the food industry, in other industries, for various reasons, but in regards to pharmaceutical manufacturing, that has not happened yet. It's progressing now slowly through some CDMOs, but it has had a very slow progress there. And the fact that we are using high pressure, that poses safety concerns. Also, other challenges in regards to the technology scalability, but certainly safety concerns when you're scaling up a process that uses high pressure. So that's one of the reasons, one of the various reasons why there has been a slow implementation, a slow adoption by the pharmaceutical industry on this. So my talk is about converting conventional batch processes that you use supercritical CO2, converting those into a continuous process. Ideally, instead of scaling up high pressure reactors, will be scaling down. So this is just it's an approach that will potentially help to adopt supercritical CO2 technology in the pharma industry. So just moving along, so that I'm conscious of time, we don't have any further delays here. So I'll just provide a very relatively brief introduction on the issue of poor solubility and poor bioavailability of pharmaceutical drugs and of new chemical entities, new pharmaceutical drugs that are coming up into the market. And comparing and then addressing the different types of technologies that are there in the industry or that have been addressed in the literature, but not necessarily being adopted by the industry. And that relates to top-down methods and bottom-up methods. Afterwards, I'll just go through supercritical CO2 technologies and the three major roles that carbon dioxide play in most of those technologies, either as a solvent, as an anti-solvent, or using CO2 as a spray enhancer. And then I will talk through CM Nano, which is a technology that we have been developing here in my group in collaboration with other collaborators within the Bernal, and that relates to the production of nanoparticles there. I'll just try to pick up here the laser pointer. I think it was here somewhere. Okay, here it is. Yeah. So moving along without any further delays. So one of the big issues within the pharmaceutical industry is that most of the drugs that are coming out from the R&D pipelines are poorly soluble, and that ultimately impacts the efficacy of those pharmaceutical drugs. So poor drug bioavailability, which is linked to poor solubility or poor permeability, is one of the major reasons why drugs fail in clinical trials. So that means that if you look here into poor bioavailability, I know the source used here was 11 years ago, but this is still represented currently within this year. Most of the drugs are poorly bioavailable, and that relates to the type of classification systems that they are inserted in. So there's the BCS, that's biopharmaceutical classification system, that groups drugs into 4 different groups, and that means those 4 groups are dependent on the permeability of the drugs, but also on the solubility as well. So class 1 drugs that belong to class 1, they are very highly soluble and highly permeable. So those do not present any major issue. Those that belong to class 2 and class 4, those are poorly soluble. Solubility is very low in water, and that will impact ultimately bioavailability. In class 3, drugs are highly soluble, but they have poor permeability. But typically, the major issues are with class 2 and class 4 drugs. If they are poorly soluble, inevitably, that might end up with poor bioavailability. So pharmaceutical companies need to come up with solutions to address those drugs which have poor solubility. If you look into class 2 and class 4, there are many different approaches, formulation approaches, that are used to improve the solubility of those drugs. So if you look into class 2, that means the drug is poorly soluble, but highly permeable. So if it's poorly soluble, one of the ways, and which I'm addressing here in this presentation, is taking the pharmaceutical drug and reducing the particle size further and further into micron size particles or nano size particles. So the smaller the particle is, the quicker it will dissolve, and it will also impact some way in the apparent solubility, in the kinetic solubility. That is moving particle size reduction from micron size to the nano size drug. But then there are also other formulation approaches, which mean generating amorphous forms of the drugs, generating amorphous solid dispersions, where the drug is molecularly dispersed within the polymer, and that will help to improve the solubility of the drug. There are also complexation approaches using lipid formulations and so on. But certainly particle size reduction is one common approach that is used even in the industry to improve the dissolution rate of the drugs. And then for class 4 drugs, it's even worse because it's poorly soluble and it's poorly permeable that those drugs are. So certainly most of those techniques are used there. But certainly in regards to particle size reduction, is very important. And particularly if the drug is very, very poorly soluble, one might consider producing nanoparticles of those drugs, because nanoparticles will have an increased surface area, and that will impact on the dissolution rate. So just looking here at some graphs from some papers published in the literature on drugs which have relatively poor solubility. So micron-sized particles of these drugs here. Now, these are model systems. Docetaxel, if I'm pronouncing it well, it's an anti-cancer drug, and we see here that microparticles. And this is not dissolution rate in water. This is the plasma concentration. So when this drug is administered, how much will be absorbed within the body. So we see here that for microparticles of this drug, the plasma concentration is relatively poor. But if we convert microparticles into nanoparticles, then the plasma concentration goes into much higher levels. And the same here for this drug over here. So going from micron-sized particles to nano-sized particles will ultimately impact bioavailability. It's not as straightforward, but it certainly has a strong impact there. Now, there are many methods that to produce micro-sized particles or nano-sized particles. One of those methods is using bottom-up methods, which is producing particles from clear solutions. And there are different methods that are used. depending if you want to produce small size particles in a nanometer size scale or in a micron size scale. We can use liquid solvent precipitation, supercritical CO2. One common method that is used within the pharma industry is called spray drying, which we are addressing here today. And spray drying is more typically used to produce microparticles rather than nanoparticles. So the spray drying is very much well implemented in the pharma industry. But it is a bottom-up method, which is we take a clear solution, we spray this solution into small droplets. Those droplets will dry and convert into particles. So spray drying is a method that is used in pharma industry, but for microparticles, not nano. Nanoparticles, those methods are still very much implementation is still slow progress in the pharma industry. Pharma industry, they have very much implemented very well top-down methods, which is taking large particles of our pharmaceutical drugs, and I'm referring more to small molecule APIs, and milling further and further into the micron size scale or into the nano size scale and producing those drugs there. Those methods are scalable, but they are highly energy intensive. So there are several challenges there as well. So if you look into this, figure here, but in a different way, we look into top-down methods where high pressure homogenization is used. For instance, when particles, micro-sized particles are used, they are pushed into a piston, and so these particles of the pharmaceutical drug are suspended in a liquid, typically water, because they are poorly soluble in water, but those are pushed in through micron-sized fluidic channels, and they are broken apart using cavitation methods. So these particles are being grinded further and further and further until you reach the desired particle size. So the smaller the particle size is, typically the better will be its dissolution. So that's using or suspending pharmaceutical drugs in a non-solvent, or we can also use dry milling, which is using different methods to here it's just a representation of bead milling, where you're using stainless steel beads to grind your particles in the rotor. So your particles, which are pharmaceutical drug, they are being broken down by these stainless steel beads. This is typically efficient if you're targeting the micron size range, but if you want to target nano size range, we have to go this way over here. So these are methods very much well implemented by the industry, but then bottom-up methods, not much has been used there. Now, these methods here, like spray drying and freeze drying, they've had a very high adoption by the pharmaceutical industry, but not necessarily for nanoparticles there. And what I'm focusing here today is on using supercritical fluids, particularly for production of particles. Now, one method which has been used very fairly in the pharmaceutical industry for small molecule drugs, it's combining a top-down method with a bottom-up method. That means they take a pharmaceutical drug which is very poorly soluble. They suspend the pharmaceutical drug in a non-solvent, a solvent that cannot dissolve the drug, and they grind it further and further using high pressure homogenization. That suspension of the drug is passed through microfluidic channels. It's broken apart into smaller particles and so on. They do numerous different cycles, and the more they do, the more the particles are broken down. And then afterwards, they need to remove the solvent from there. And what they do is they add a polymer there. The polymer is dissolved in the solution, but not the API, and they spray this and convert this into nanoparticles there. Now that's more or less the standard what's out there in terms of the literature and the industry implementation. And what I'm addressing today is really the different supercritical CO2 technologies. So there are many variations and many different types of techniques, but I'm going through the major ones, the more conventional ones, which each use one of three different properties of supercritical CO2. And the first one is using CO2 as a solvent. So when using CO2 as a solvent or as an anti-solvent, we typically use the properties of CO2. And it's important to note that these methods do not generate carbon dioxide, right? They are neutral. They use existing CO2 and they compress CO2 and they use it for processing and then release it afterwards. So they are neutral. We are not generating CO2 with these methods here. And there are many fluids can be compressed into a supercritical fluid. CO2 is one of the most used substances has a supercritical CO2 because you don't need much high temperatures to reach supercritical state. If you look here into the phase diagram where we have pressure and temperature, so you have here the different phases of CO2, solid, liquid, and gas, and you need to reach beyond the supercritical, the critical point for CO2 to become a supercritical fluid, so that there's no distinction between liquid and gas, and both merge into a supercritical state. So that means 31 degrees Celsius for CO2 to become supercritical, and about 73, 74 bar. Above this, supercritical CO2 will have properties of a liquid, but also of a gas, but it's neither a liquid or a gas. And that confers very interesting properties for CO2. That means that CO2 will behave as a liquid. It will have a liquid-like density and a liquid-like diffusion as well, but the viscosity will be like a gas, and that will be very important to process pharmaceutical drugs. And also, if you're dealing with from drugs which are sensitive to temperature, it is interesting that we don't need to go to 100 degrees or further. We can use temperatures above 31 degrees Celsius to process pharmaceutical drugs. Now, one of the main categories, one of the first of the three main categories using CO2 is using CO2 as a solvent. And by using CO2 as a solvent, there are different ways that we can process pharmaceutical drugs. It's more difficult to produce nano-sized particles, but we can indeed produce micron-sized particles. And this is one method that I've used before a few years back. And what we are doing here, we are using just one API. We're putting an API powder, pharmaceutical drug, as a powder inside a high-pressure vessel, and then closing it without adding any liquid organic solvent, and then pressurizing with CO2. And we could do this in a different way, in two different ways. One is we could use an API which is highly soluble in CO2. That means as soon as you start pressurizing the vessel with CO2, the powder will be dissolving into the CO2. And then you could precipitate the powder in a way that you could control the polymorphic form that you are obtaining. And the other way we are doing it is that the API does not necessarily have to have high solubility in CO2. And in fairness, most pharmaceutical drugs do not have good solubility in CO2, and that is the issue. So taking an API which has, even if it's a very minimal, very small solubility in CO2, we're actually producing co-crystals, which is producing new crystalline entities of a pharmaceutical drug, a model pharmaceutical drug, with a coformer or an excipient. So those two will be linking together and generating a new crystalline form. So the way it was operating here is we are actually filling up the whole of the vessel, right? We are doing this at different scales, but all at lab scale. So we were filling up the vessel with powder of the API and the coformer. Both powders were there. CO2 was coming inside. We were pressurizing the CO2 up to 100 or 200 bar, but the powder was still there, so the powder was not dissolved. Maybe a small amount of the API and coformer were being dissolved, but most of the powder was there. So we were creating a slurry of the powder of these two compounds in CO2, and then steering this over time. So the API and the coformer were linking together. They were generating co-crystals of each other over time, over and over. So in this way, we could fill up all of the vessel and leaving some space here for the CO2 or for the powder to be able to move. And we are converting this into high pressure vessel. Now, obviously, if you need tons of product, this is an issue because, you know, if this works well, if you're using a 1 liter vessel, if you want to scale it up to 1,000 liters vessels, that means you have a 1,000 liter high pressure bomb. That's an issue for the pharmaceutical industry, certainly. That's using this as a solvent. There's a company called Nanoform, and those guys are from Finland. They are spin out from the University of Helsinki. They're spin out in 2015. And in the first 4 years, they have generated 17 million euros, and they have created 7 pharmaceutical lines in their company. One of them is GMP approved. And now recently they went into a public audition and they have generated 80 million euros. And it's all based on this particular technology, using CO2 as a solvent. But here they do it in a different way on what I was describing here. Here, everything happens in a high pressure vessel. And the way they are doing it, they have taken a conventional method from supercritical CO2 and converted it into something better. In this case, what they have here is they have a high pressure chamber. So they take a pharmaceutical drug, which is typically poorly soluble. They put poorly soluble in water. They put it in the high pressure vessel, and the CO2 will fully dissolve. Now, this only works for molecules for pharmaceutical drugs which have high solubility in CO2. So for those that have higher solubility in CO2, they pressurize the vessel with CO2. CO2 will fully dissolve the API, and then they open the valve, and this is all under high pressure, and this is pushed here, right? And it goes through a nozzle, and then this goes into a drying chamber, which is at atmospheric pressure. So the pressure is only here. So they are generating microparticles or nanoparticles. But what the novelty here is that it's not depicted here in this figure, but they have here on the drying chamber, they have here several inlets of CO2, right? This is also an inlet of CO2 that CO2 comes with pharmaceutical drug dissolved there, but this is heated, right? So the spray comes out at 50 degrees or 40 degrees, but then they have here inlets of CO2, high pressure CO2, which is not heated. What happens here? If it's not heated, CO2, when it goes from high pressure to low pressure, it loses heat. If it loses heat, it converts into dry ice, right? So they put here showers of CO2. So they're actually generating snow, dry snow. And this dry snow, as this is spraying here, it will catch the particles that are coming up from here. So the drug is dissolved in CO2 at high pressure. When it goes to low pressure or 1 bar, the CO2 cannot dissolve anymore and the particles will precipitate. But if they are very small nanoparticles, they are very difficult to collect or isolate. So in this technology, they put dry ice here. So they form cloud of dry ice CO2, and it will freeze the particles here. And they are actually building a snow here, snow made of CO2, right? And then this will convert, this dry ice will convert into vapor and CO2 will be released, but it's the way that they have used to collect efficiently nano-sized particles. So this technology has generated 80 million euros for the company, which is impressive, and they're very much progressing further implementing this in the pharmaceutical industry. So they're very much changing the I suppose the success, the low success that the CO2 has had in the pharmaceutical industry. Now that's using CO2 as a solvent, right? Now using CO2 as an anti-solvent, some of the methods that we have been used in our labs here in our lab facilities here in the Bernal is using CO2 as an anti-solvent in a very simple way, which is again taking a bottle of CO2 and compressing further the CO2 using a high pressure pump, pressurizing at the right pressure to what we want and the right temperature inside an incubating chamber, and then the CO2 will be inserted into a high pressure vessel, right? So in this high pressure vessel, we put a certain amount of a solution which contains a liquid organic solvent and the pharmaceutical drug. We have generated a solution, and then we are using CO2 to precipitate, to supersaturate the solution of the drug and to precipitate the particles there. So CO2 comes along, it mixes with the drug solution, right? The CO2 should have a good affinity with the solvent where the drug is dissolved. And then CO2 will saturate the solution and extract the solvent, and the particles will eventually precipitate. So this is a method that is used to produce microparticles. We cannot produce efficiently nanoparticles here. It's difficult to control the size, but we can control the polymorphic form here. So this is a batch approach, right? And this is a conventional method to use CO2 as an anti-solvent. And there's a semi-continuous approach also using an anti-solvent, which is called SAS. And this is a method that some CDMOs have generated equipments over the last 10 or 20 years. But again, no implementation in the pharma industry. And that uses also CO2 as an anti-solvent. But here, CO2 is pumped into a high pressure chamber and liquid solution as well through a nozzle. So this nozzle will push the solution. The solution is sprayed into droplets. Those droplets will go inside a high pressure chamber. That means that the CO2 here will penetrate the droplets, will extract the solvent, will supersaturate the solvent, and then the particles will eventually precipitate here. But this is all under high pressure. So if we need to scale this up from lab scale to pilot scale to industrial scale, it's very complicated. It's complicated to maintain the homogeneity of the droplets, the size of the droplets, the homogeneity of the CO2 dispersed in the chamber. And obviously, the larger is the chamber, the larger is the high pressure vessel, the more challenges or the more risks it imposes in regards to safety concerns. So one of the novel ideas to use these technologies is to get rid of the high pressure here in this chamber, similar to what Nanoform were doing here before. and that's using atmospheric pressure here, but using instead high pressure in the nozzle. So getting rid of the high pressure inside the drying chamber, because CO2 is used here to precipitate droplets, precipitate particles from droplets, and getting rid of that. Now, just a note that using this type of methods, using CO2 as an antisolvent, you typically can control very accurately the polymorphic form that you produce for your drug. And there are even drugs where you generate new polymorphic forms that are not reproducible by using any other techniques. Those some examples here from the literature, using some pharmaceutical model systems where new polymorphic forms were generated that they were never being produced by any other conventional techniques, crystallization or liquid and solvent precipitation and so on. So it was due to the particular properties of CO2 and the high pressure there. So converting this into atmospheric pressure spray drying method will be the way to go. That's what our group has been using, which is converting a batch process that I was using before, where everything happens in a high pressure vessel. So if you want to scale it up, you need to scale up the size of the vessel, or using a SAS process like before, that you're spraying this drug solution into a high pressure chamber. We are converting this in just a coaxial nozzle, and we're using a conventional spray drying. No pressure inside the drying chamber. The pressure is only used here in the nozzle here. So here in the nozzle, we have the CO2 going from the sides, the drug solution coming from internally, and then high pressure, it's occurring here. This is sprayed into an atmospheric drying chamber. So we are using the CO2 anti-solvent effect. So the CO2 is mixing here with the liquid, supersaturating, but then precipitation will happen afterwards without having to have a high pressure drying chamber there. Some examples of particles which can be produced, or nanoparticles produced using this type of technology. On the left-hand side, we see here protein model systems here, lysozyme, BSA, and so on. And then on the right-hand side, we see small molecule pharmaceutical model systems. This is one of the small molecule APIs that we have been working with to produce nanoparticles, amorphous nanoparticles or crystalline nanoparticles. And we had a student there in the group that he was working there afterwards as a postdoc, that he was working with different API model systems. And one of them was indeed carbamazepine. And the way he was doing this spray drying method, where indeed there's no high pressure here inside the drying chamber. The high pressure is just located here inside the nozzle. And in this case, we have here this technology where we can control the polymorphic form of carbamazepine, of this drug, which is being produced here by controlling the conditions inside the nozzle under high pressure, temperature, CO2, and other things as well. So we are controlling the nucleation of the polymorphic form. And then afterwards, as droplets were being produced, this spray, we were producing the right polymorphic form. Just as an example, we have here powder X-ray diffraction of this pharmaceutical drug, carbamazepine. And depending on the even using the same processing conditions in using the CO2 spray drying system, which is pressure, temperature, flow rates, all the same, but just slightly changing the amount of surfactants that we are using in the drug solution, we could tweak the polymorphic form, right? So we see the theoretical patterns for form 1, form 2, and form 3 for carbamazepine, so published in the Cambridge Structural Database. And here we see the different forms produced by this technique just by changing the conditions inside the nozzle. In this particular case, just changing the amount of additive added to the drug solution before the process. In this case, we didn't use any additives. We were getting form 1, but using different additives here, 5% SDS or sodium stearate, we're getting form 2 or form 3. So XRD pure forms of this API. So again, this was just an overview about the different technologies using different roles of CO2 there, and just presenting here without much delay here, a technology that combines some of those methods into for the production of nanoparticles, and at the same time isolating, collecting those nanoparticles, which is a challenge, because when we are dealing with nanoparticles, the smaller they are, the more difficult they are to handle, to collect, and to process into a final dosage form, like a tablet or a capsule. So this is one of the technologies that we have been developing in the group, which is called CM Nano, It has been mostly funded by Enterprise Ireland. And in this technology here, we went from using batch supercritical process, which is use high pressure vessels to conduct our experiments on producing microparticles, and converting these into continuous spray drying process, which is instead of scaling up the high pressure vessel, we are actually scaling down the high pressure vessel, converting this into a nozzle, right? Where the high pressure only happens here in the nozzle. But then the challenge we are facing there is indeed we are controlling the polymorphic form of the API, we are controlling the size, but then how do we collect nanoparticles? The yield of this process here, the collection yield will be around 10%, which is very low, or 20% at the best. So the new technology that we are doing here is somewhat a conventional spray drying process that uses CO2 in the nozzle, high pressure CO2 in the nozzle, such as here. But then we were combining into a collection mechanism that I'm going to explain in the next slide, which is we are spraying droplets, and those droplets will be drying, and those droplets, as they are dried, they are converted, the API is converted into nanoparticles. So those nanoparticles will be coating micron-sized excipients here that they were laid out on the top of a mesh here, which was placed in the middle of the drying chamber. So just take note that the drying chamber is at atmospheric pressure. The pressure was only happening here in one nozzle here. I will explain this in a bit better way in the next slide. And then using a single nozzle, we are converting these into a multi-nozzle system, where in this case, the CO2 comes from here and the API solution comes from here. We are just using one single nozzle here. But to scale up, we are using multiple nozzles. And these nozzles here, instead of being placed here and on the top, they are placing here on the walls. And what we are having here is we are putting excipient, micron-sized excipient particles here through a hopper. These excipient particles were falling down by gravity. As they are falling down, they are being coated with nanoparticles from the different nozzles here. So you end up with a nano formulation that is composed of large micron-sized excipient particles, but they have nanoparticles coated there. And then it made this very easy to collect nanoparticles, because in fairness, they are micron-sized dispersions. Nanoparticles are part of that process. So this technology here, which is a batch semi-continuous process, it consists of putting CO2 from one side, the API solution from the other side. They will mix here in the nozzle. We can induce anti-solvent nucleation here, or make it just very simple, just using CO2 just to spray, and droplets are being formed. High pressure here, atmospheric pressure here in the chamber. And then those droplets are being dried, nanoparticles are being formed, and those nanoparticles are coated onto micron-sized excipient particles here, which are located here in the drying chamber. And those are being kind of fluidizing here. As soon as this is done, all of this is discharged, and we have here a nanoformulation. So we have here controlled nucleation here using the CO2 and the solvent effect. We have atomization and drying of nanoparticles, coating of nanoparticles onto micron-sized excipient, and then discharging these API nanoformulations. So this allows us to produce and convert nano-sized particles into a formulation that can be directly compressible into a tablet, right? And this in theory allows us to convert a typical pharmaceutical manufacturing footprint that goes from crystallization to filtration, drying, milling, to break down the particles, the crystals, into the right size, and so on, until you end up with the finished product, converting these into a manufacturing footprint which has much less unit operations. So Matteo, we have what, 2 minutes left?
Yeah, 2 quick minutes.
Okay, so I'll just go here to some of the results here very quickly, which is we have used some of APIs here using our CM nanotechnology, which are poorly solvable. So BCS class 4, BCS class 2 APIs, and also BCS class 4, all poorly solvable. So producing nanoparticles of these APIs and converting these into nanoformulations which contain the API coated onto our excipients. So without spending much time here, just showing 3 APIs which are BCS class 4, we are producing very small sized nanoparticles of these APIs, right? Between 100 and 500 nanometers, okay? And controlling the polymorphic form that we're obtaining. And the yields obtained here, the collection of these APIs in this spray drying process were very high, okay? Typically in the conventional nano spray drying process, the yields are 10%, and here we have 75% and so on. So we are producing very small nanoparticles and with very high yields. And then this comparing just with conventional spray drying. Conventional nano spray drying, you cannot go much lower than 300 nanometers, and here we are going much lower. And then comparing our collection yield, okay, we are going from 60 to 90% yield. Conventional nano spray drying, you'll have 10% yield or 30% yield. Now, some of those results, in the interest of time, I won't show it. These are just showing the images of the nanoparticles coated onto excipient particles. In this case, was microcrystalline cellulose. Okay, just going here into compressibility. So we have nanoparticles which are highly compressible, have good compressibility. That means that our powder of these different APIs, right? This is MCC, which has good compressibility, the excipient particles, and this is the API coated onto MCC, okay? All these different APIs, and they have all good compressibility here. So typically nanoparticles alone, they cannot be compressed into a tablet, and those can. They also have very good dissolution rates, okay? If you compare it with the raw API, has very slow dissolution rate, but our nanoparticles have, although they are micron size formulations, they still have nanoparticles there of API, and they dissolve very quickly there. Okay, this is just a resume of the CM Nano, but just to finalize in terms of the potential of the CO2 technologies there, and the trend has always been over the last 10, 20 years to scale up high pressure vessels, and that has always been in the wrong direction because scaling up is an issue. Pharma companies will never take that on. And this is one of the approach that can help, which is instead of scaling up, scaling down, converting high pressure vessels into spray drying nozzles or converting these into tubings where you can mix CO2 or an anti-solvent under high pressure with the solvent and so on. So instead of scaling up, you can scale down, and at least you sustain some of the safety issues there. So just as the conclusions there, converting batch process into a continuous process, it's something that will certainly help high pressure technologies to be adopted there by the industry, but certainly using small installations instead of using high pressure vessels will certainly be something that will help these promising technologies to be adopted by the industry. So just to acknowledge my current group members within the group and also past group members that have already left, and also all the collaborators within SSPC, PMTC, the Bernal, and also external collaborators there, and also thanking the funding agencies for the funding support there. And that's all. Thank you very much for your attention. If you have any questions, please shoot those questions to me.
Thank you, Luis, for very nice and clear talk. It was very intense and probably should have had more
a lot of information.
time and space, yes. But I think you gave a good idea of what you do and what the directions of this research is going to be. Is there any question from the audience? I do have a couple of questions myself. So first one is a technical question. Is it possible to use any other fluid other than CO2 in a supercritical? And I know that some gases can easily become supercritical, like methane or propane.
Yeah, you can use ethane as well. Some of those gases are flammable, and that imposes safety issues. Mm-hmm. Many fluids, many substances which I can convert can be converted into supercritical fluids. You need to use much higher pressure. So you see here, you only use 74, only 74 bar, but sometimes you have to use with some fluids 200 bar. Now, CO2 is used, nitrogen as well. Nitrogen, I think the pressure to convert into supercritical CO2 is even lower than 74 bar. The problem of nitrogen is very much used, but nitrogen does not have solvent capacity that CO2 has. So nitrogen is mostly used just as a spray enhancer. CO2 gives other possibilities. Water can be used as a supercritical fluid, but you need to go over 300 degrees Celsius, and that's that can be a challenge, I suppose.
Okay. And another question, more practical. When you spray dry your API onto your excipient, what's the load of drag into the excipient?
Yeah, at the moment, this was work done by Vivek, one of the former postdocs in my group. The load was 10% and 20%, and he was exploring up to 40% loading. And the challenge there on using 40% loading is that using So you see here, those results are for 10% loading of the API onto an excipient, in this case MCC. So he was exploring, it could go up to 40%, but he was having issues sometimes with homogeneity of the coating of the API onto the excipient particle. So that because the issues there with the batch process is, or the semi-continuous process, is that to have a higher loading, either you increase too much the excipient, the amount of excipients here, and that might it's a challenge, or you need to spray for longer. The continuous technology, so this is the batch, the continuous technology allows us to go to much higher loadings, but we have not developed that work yet. That means the excipient particles are falling down, they are being coated, and if needed, they can go back and recirculate and coat further. There will always be a limit to which you cannot put more loading. Otherwise, you'll need to have a very thick loading of the API onto the excipients, and that's not ideal.
One question from Ahmed, what is the average duration of the process?
The supercritical spray drying depends how much powder you produce. Typically, we are in the milligram scale for just using one nozzle. But if you are using the CM Nano, which is API onto excipients, we can take maybe a couple of hours because at the end you have excipient and API, so we can produce about 18 grams per every 2 hours, if I'm correct. API and excipient there.
Another question from Vasant, is there any way to get the value of supersaturation? I don't know what supersaturation of what respect to what. I don't know, maybe you know the question.
No, when you mix CO2, like how do you measure the supersaturation exactly?
Yeah, we cannot measure directly into the nozzle, right? What we do is in the high pressure vessel, in the batch vessel, we try to use the same. So here we use amount of CO2 and the amount of solvents and API, and then we measure and then we pressurize this with CO2 until we see slowly precipitation of the API. So we see what's supersaturation there. But in the nozzle, what we use here, we have flow rates. We don't have quantities. We have flow rates, or right, quantities over time. So we can convert these, molar ratios of CO2 to solvent into flow rates here, but we cannot measure directly supersaturation here. Okay, we can understand more or less if particles precipitate in the nozzle, because then the nozzle gets blocked, so we know where precipitation is actually happening. But measuring accurately supersaturation is very challenging because it's under high pressure.
So you think you have a supersaturation if there is a phase change? So that's how you conclude, or?
Yeah, so if there is a phase change, if you allow this for a phase change to happen, I mean, we can have a two-phase system here, right? You can have supercritical CO2 and liquid solvent, and they might be still separated. It might be just two phases, but we can use conditions where CO2 mixes with the solvent and it's just everything in one phase, right? But it all depends on the solubility of the API in the solvent, on the solubility of the API in the CO2, and the solubility of the API in both the CO2 and the solvent mixture. So we can assess those conditions accurately here, but then reproducing this here accurately, it's a different challenge. Yeah.
Yeah. Okay. Well, thank you.
Okay. There's some other question, Luis. I ask you please to answer privately or to meet with Francisco, because for time requirement, I would like to move now to our next speaker. Thanks again for the talk.
Thanks.
Judging by the question, people were very interested in this, and probably should have more of this. With this, I want to thank you again and welcome Kartik, which is our next speaker. Kartik is a postdoctoral researcher in the Confirm Smart Manufacturing Research Center here in the Banal, and he joined the University of Limerick as a Marie Curie researcher, and is working with Professor Conor McCarthy, Professor Michael McCarthy, and Dr. Ronan O'Higgins. And he will discuss his work on how to join together composite and metals materials. So, Karthik, you can, thanks again for being here. You can share your screen. We cannot hear you.
Can you hear me now?
Yes, now we can hear you. Thanks.
Thank you, Matthew, for the introduction, and thanks for the opportunity to present at the Bernal seminar series. I'm sharing my screen. Can you see my screen?
Yes.
Right. Get on to the presentation mode. Just moving to the presentation mode at the minute. Just let me know once you can see that.
Yeah, we can see it.
All right, perfect. Thanks again, Matthew. I'm Karthik. Good afternoon, everyone. My PhD research was on novel. Sorry, just plug the laser. Yeah. Good afternoon, everyone. I'm Karthik. My PhD research was on novel through-thickness reinforced composite metal joining technology. And this project was funded through a larger Marie Curie ITN project called the ICONIC. ICONIC stands for Improving Crashworthiness of composite transportation structures. At this instant, I thank my supervisors, Professor Connor McCarthy, Professor Michael McCarthy, and Dr. Ronan O'Higgins for their supervision and guidance throughout the course of this research. This will be the overview of my presentation today. I'll briefly introduce the topic, then I'll present an interesting case study which demonstrates how fragile can adhesive joints be. Then I'll move on to the novel joining technology, summarize the performance advantages, and introduce a scalable manufacturing method. Finally, I'll conclude highlighting the key findings of this research work and give future directions to the work. Now, this is a crash test between a 2010 sedan and a 1957 sedan. Now, it is important to note the amount of intrusion into the passenger compartment. Probably a passenger in a 1957 sedan might not have survived, whereas in a 2010 sedan, since there is no intrusion into the passenger compartment, the passenger would still be harmed, but not critically. So this highlights the engineering advancements that were made in the past 5 decades to meet the crashworthiness requirements of automotive industry. Now, lightweighting and emissions are two most common things that we hear often in composite research. But if we look at what was the percentage change in weight and emissions from 1975 until 2020, we see that the weight of the vehicle have relatively remained the same in the late 2000s as it was in 1975, whereas the emissions have reduced considerably, and the fuel economy has increased considerably. But we are still far away from what the regulations demand, which is about 95 gram per kilometer, whereas we are still at 200 gram of CO2 per kilometer. Now, if we look at what different material goes into the construction of a typical car, now we see that the amount of steel has considerably reduced. The high-strength steel has increased, but if we look at the amount of plastics that gets used in a typical construction of the car, it has marginally increased. This highlights the huge lightweighting potential using plastics and composites. But the question is, what limits the successful design of multi-material structures? Several research institutes around the globe have pointed to joining solution, the lack of understanding and the lack of development of joining solution for multi-material structures to be the high priority research need. Again, most agencies rate these joining technologies next to just the high productivity processing of composites. What is the state of the art currently? If at all the composites are being used in primary load bearing structures, they are just used as an insert into an existing metal component, just so as to reduce the sheet metal thickness, add stiffness and strength while reducing the mass of the component. There are two major joining techniques when we are looking at joining two different materials. One is mechanical fastening and the other is adhesive bonding. Both have their own advantages and disadvantages, especially with respect to composites structures. Now, what is this joining technology about? This joining technology combines the advantages of adhesive joining and mechanical fastening methods. Now, in this joining technology, we have the interlocking features that are machined onto the aluminum adherent, and equivalent depressions are molded into the composite adherent. In addition to the interlock offered by the mechanical interlock offered by these features, we also have a suitable adhesive that bonds the metal and the composite adherent. A typical cross-section of the technology that we are talking about would look like that, where we have the interlocking metal feature mating with the interlocking composite feature. Now, slightly deviating from the novel joining technology, I'd like to present a case study where we had very interesting results. What is an adhesive spew? It is just the excess adhesive that is squeezed out of a joint when we manufacture a joint. And what is the load eccentricity? It is defined as the eccentricity between the applied force and the reaction force. And this is a particularly a problem when we are looking at single lap joining configuration, which is the most research joining configuration for use in industry. Now, though spew and eccentricity coexist in real structures, what we do at lab scale testing is that we introduce spacers at the end of the joints to minimize the effect of eccentricity, and we get rid of the spews so as to get rid of the effect of spews. But can they affect the mechanical performance? But if so, to what extent? That was the question that we tried to address in this particular research. Typically, if we look at a spew that is naturally formed, it takes a half-rounded shape. And what we did was we did a systematic study where we systematically changed the eccentricity by changing the thickness of the spacer that are bonded to the ends of the adherent. And we let the spew take its natural shape, which is the half-rounded shape. Now, as we saw in the first slide, where these joints are supposed to be used in crash-worthy structures, so we need testing at quasi-static in-service loading rates and dynamic crash loading rates. Lab shear strength and energy absorption, which is also called as work to failure, are two major parameters that are used to quantify the mechanical performance of a joint. Now, on the right, we have the lab shear strength and work to failure for the different tested cases, the top being the quasi-static test and the bottom two being the dynamic test at 0.5 meters per second and 3 meters per second. Interestingly, what we saw was there is a 22% and 13% decrease in strength and 50% decrease in energy absorption when we are looking at the effect of eccentricity. And accidentally, there's a bit of lag. Accidentally, we found a new spew geometry, which was achieved just by pressing the half-rounded spew geometry into a flat shape, and we call it a flat spew. And since we do that only at one end of the composite, at only one end of the overlap, we call it a hybrid spew geometry. And this hybrid spew geometry improved the lab shear strength and energy absorption to a great extent. Now, for people who are interested in why and how, we ran an extensive numerical analysis using finite element analysis, and we ran digital image correlation to look at the effect of different spew shapes. I wouldn't go into the details of it just for the interest of time, but if something that is if the excess adhesive that is many times aren't considered in the joint design can affect the performance from minus 50% to 120%, I will leave the effect of more important parameters that are considered during joint to your imagination. So that is basically the question on the reliability of bonded joints when used in primary load critical structures. Now coming back to the performance of novel joints, this is again the first comprehensive study between thermoplastic composites and the aluminum joints, employing macroscale interlocking features. Again, these joints were tested at both quasi-static and dynamic loading rates. Now, comparing the force deformation curves that presented in the left corner of the slide, the black color lines correspond to the baseline joints without any interlocking features, and the red lines correspond to the novel joints, which we call it as interlocking adhesive joints. As we can see, there is a small increase, a reasonable increase in the peak loads, which converts into the increase in lap shear strength, and there is a massive increase in energy absorption, which is calculated as the area under the curve. So this reflects on the lap shear strength and work to failure. Our lap shear strengths on an average improved by about 10%, whereas our work to failure at 0.5 meters per second improved to about 120%, and whereas at quasi-static was at about 75%. But looking at just these curves, we do not get any insights into the damage and deformation mechanisms. But we know that adhesives are strongest in shear what we can peel. Now, we also know that the eccentric loading is going to cause a moment and a shear force at the overlap ends of a joint. And these moments can cause overlap rotation, and overlap rotation means peel stresses. And peel stresses are primarily the reason for damage initiation and involution of bonded joints. Now, when we look at this in more detail, this is the first time someone has managed to connect these dots together and make sense of the data. So we used a simple cosine law to continuously monitor the overlap rotation. And this is the result that we had. So in this, you can see the continuous line correspond to the continuous lines correspond to the force deformation curves, and the dotted lines correspond to the rotation deformation curves. Comparing the black ones, which correspond to the baseline joint, and the red ones that correspond to the interlocking joints or the novel joints, we see that the rotation is significantly minimized when using an interlock joint, and that results in a very high energy absorption and improvement in the strength, as we saw in the previous slide. So this gives a solid interpretation of the deformation and damage mechanisms in the interlocking joint, and anything that is pointed to as 1, 2, and 3 represents an important event that is summarized in the schematic shown in the right. 1 corresponds to the plasticity initiation, and 2 the primary crack initiation, which usually happens at the free end of the composite adherent, and 3 being the secondary crack initiation at the opposite end to the composite free end. Now, the failure modes can be of different types, and it highly depends on how these failure mechanisms interact with one another. Now, we also conducted a full field strain analysis using digital image correlation, and I present the results here in this box. I wouldn't go into the details again, but in the interest of time, but we had quite a lot of interesting observations on how the primary crack initiates, and it is restrained by in compressive stress zone within the interlocking features, and causes the secondary crack to initiate, which propagates faster. So this is some details, and we have a lot of interesting results which we have summarized in this publication down there. One of the things that was bothering me was the drastic decrease in the energy absorption when we moved from 0.5 meters per second to 3 meters per second. This was actually accompanied by a composite adherent failure. And that was a video, and the video is shot at about 100,000 frames per second. For some reason it doesn't play. Okay, I just skipped the video. And the second thing that was bothering us was the manufacturing method. The current manufacturing methods cannot be scaled up to an industrial production scenario. So we looked at different manufacturing methods for manufacturing the composite adherent. One of those that we looked at was simple stacking, where we had the fabric composite laid on top of the mold tool. And the second one was a molded in manufacturing method, where we preformed the yarns around the interlocking features. The third one was a cut fiber manufacturing method, where we intentionally cut the carbon fiber composite at known distances to generate discontinuous fibers. Interestingly, what we found was that the fiber cutting method resulted in the best mechanical performance. I know that this will raise a lot of eyebrows within the composite research because cutting intentionally damaging the fibers, but we have an explanation here. Now, we did another image processing analysis where we looked at the transverse deflection of the adherents. And as we know that the maximum bending moment is going to exist at the free end of the overlap, the maximum transverse deflection is going to exist there. But as the crack propagates, the maximum transverse deflection moves into the overlap region. And if a composite damage occurs because of the transverse deflections of the highest bending stresses, then we kind of generate a signature of a damage. And whereas if it doesn't, we have smooth curves, which shows that there isn't a damage. And looking at the problem that I stated 2 slides ago, the composite adherent failure at 3 meters per second, as soon as the maximum transverse deflection progresses into the overlap zone, a failure occurs, which kind of opens up on the question on the fiber volume fraction. Now, the fiber volume fraction is actually the secret recipe. That is manufacturing method 1, which is simple stacking. The second is the mold-in manufacturing method. The third is the fiber cutting method, and these are all optical micrographs. This is along the width of the joint, and this is along the length of the joint. And what we see here is that as we move from method 1 to method 3, we have a uniform fiber distribution, which means that we have a higher bending stiffness when we use a fiber cutting method, and this caused a failure either in the metal adherent or in the overlap and improve the energy absorption. Coming to the conclusions, I'll just highlight the major observations during the study. We saw that the interlocking joints have a very high energy absorption capacity, and it kind of shows a potential for use in automotive crashworthiness. One of the major reasons why bonded joints are in use in practical application is the spontaneous failure behavior. But we have shown that interlocking joints has an excellent capability to sustain the load as the crack grows. We would even be able to tailor the joint performance because in few cases we have seen that the joints are stronger than the substrate material itself, and this can even be an alternative to an intricate double lap joints, which are predominantly used in aerospace industry. And we also propose a scalable and an economical manufacturing process that suits the high productivity requirements of automotive industry. Coming to the future work, this technology needs further priming in terms of different loading conditions that we evaluate the performance for. And we also need to evaluate the alternative interlocking geometry in terms of what the interlocking feature width, thickness, length, position, and cones are. And one of those interesting things that we are making some progress on at the minute is to evaluate the performance of such joining technology in demonstrator parts. The one there is actually a demonstrator part from a EU project on Fiat Panda, and these two are the multi-material structures in BMW 7 Series. And when we get to this stage is when the OEMs will have some confidence on taking it further into their actual products. That brings me to the end of the presentation. Thank you very much again. If there are any questions.
Thank you, Kartik, for your nice talk. Is there any question from the audience? If not, I have a comment about the weight, how the weight of vehicles has changed during time. And I think that the problem is not with technology, but is with the fact that people want a big car now. So, you know, the material are getting lighter and lighter, but cars are getting bigger and bigger. Probably that's what causes cars to be heavier.
Okay. So this was the plot was from US EPA, and when they computed the average vehicle weight, they actually went by the segment. So they did not take all the cars together, but they went by a segment. So say if we are comparing SUVs, and we are just comparing SUVs alone.
Yeah, but a Mini of the 60s was much lighter than a Mini now. Was much smaller. Anyway, thanks for your talk. I think it's late. People want to go for lunch. And thanks again. I want to remind everyone that next week will be the last episode of the series, and we'll have our guest lecture. You'll receive information later in the next few days. Thanks everyone, and see you next week.